Thank you, Patrick, and welcome to my talk today, where we are going to dive into Apple's background task management. So as Patrick mentioned, my name is also Patrick. Wonderful name. I am the founder of the Objective-C Foundation, and many of you might be familiar about some of the things we do, most notably our free open source Mac security tools. I'm also the author of The Art of Mac Malware books, and the founder, the co-organizer of the Objective by the C conference. So, I always like to start my talks by talking to you about what you will learn today, because the goal of my talk is really for it to be an informal session that's educational to you, informative. So we're going to learn four main things, but I want to point out, though, that even though this talk is largely focused on Apple's background task management, we're going to dive into a myriad of other topics, such as reverse engineering, malware detection, macOS internals, exploits, detections. So really, I hope there's something for everyone. We're going to start by looking at the internals of macOS's BTM, background task management subsystem. We are then going to talk about, once we have an understanding of this framework, how to leverage it to build our own security tools. We're then going to put on our black hats, put ourselves in the shoes of offensive-minded adversaries, and talk about how we can perhaps bypass this subsystem. Because it's always good to know the limitations of any security technology. And then finally, we're going to end by talking about how we as third-party developers can write detections to detect potential bypasses until Apple gets their act together. So the way we're going to do this is we're going to start with an overview of BTM. We're going to dive into the internals of it, really get into the weeds, look at some disassembly, look at some reverse engineering. Once we have the understanding of the internals, we're going to kind of pop back out and talk about, as I mentioned, developing tools that leverage BTM. It's mostly undocumented, but as I will show you, we can actually build some very powerful detection tools. We then talk about some bypasses and finally end up with detections of those bypasses. So let's start with an overview of BTM. And first, you might be wondering, what is background task management, which I will refer to as BTM for the rest of the presentation? Well, the idea is it's the governance of persistent items, which Apple refers to as background tasks. What do I mean by persistence? In the context of this presentation, it's items that are installed so that when a macOS system is rebooted or when the user relogs in, they are automatically re-executed. This is important to talk about because, as we'll see, a lot of malware is going to persist. So BTM, and we'll dive into each of these three components in more detail, is composed of three main components, or rather actions that you can observe either as a user, a Mac admin, or as a developer writing security tools. So the first is, in recent versions of macOS with the introduction of BTM, is now there is an alert that is shown to the user anytime an item is persisted. Now it's important to note that something persisted doesn't necessarily mean something bad. So as we can see on the slide, when you install Zoom, the legitimate Zoom, it installs a persistent component. I believe it's an auto-update component that needs to always be running to check for new versions. And since that is installed in a manner that tells the operating system, please run me every time the system is rebooted and the user logs in, Apple now will generate an alert to the user. This is good, especially from a security point of view. So that's the first component of BTM that is especially observable to users. The second piece is it also interacts, and we'll talk more about this, with endpoint security, which is a subsystem that delivers events of interest to third-party security tools. And we can see, and we will see, that there is also now a security event that is delivered to any endpoint security clients. So as you can see, we can now write security tools that get alerts from the operating system when anything persists, whether it's Zoom or a piece of malware. And finally, there's also now in the UI a way where the user can see everything that is persisted. So this really makes sense. Again, Apple really says, hey, we should kind of organize persistence better, generate an alert to the user when something's persisted, generate a security event so security tools can pick up on this, and also have a nice UI for the user. So in concept, the idea of this is pretty good. And you still might be wondering, okay, well, who really cares? And the answer is, well, we do, both as defenders and perhaps as adversaries as well, or at least understand why adversaries might care. So as I mentioned, as defenders, we can leverage, as we will see, background task management to build very powerful security tools that can really go a long way into detecting persistent malware, even if we've never seen the malware before. As adversaries, or as people who want to understand how adversaries operate, the new security components can be problematic. So you can imagine a hacker now gets into a system in some way, undetected, goes to persist. Well, now all of a sudden there's two things. There's a big alert to the user, and there's this notification that's delivered to security tools. So for red teamers or for hackers, this is problematic. They're obviously going to care about BTM as well. Okay, so let's now start to dig into some of the internals of this, because BTM is largely undocumented. Unfortunately, Apple has not given us documentation on this, but makes it an interesting target, I guess, based on that. So anytime I begin reverse engineering or analyzing a piece of the operating system that I don't know anything about, I turn to the logs. And this is because a lot of these undocumented frameworks and components of macOS, even though they're closed sourced, will log all sorts of very, very useful information to the logging subsystem that we can use to guide our reverse engineering efforts, or to even gain an understanding of what they're doing without having to dig into any code. Now, on recent versions of macOS, Apple has redacted a lot of information from the log for privacy and security reasons. So the first thing you want to do on your own analysis machine is enable private logging. There's a link on the slide about how to do it. It's pretty straightforward. You basically install a profile saying, hey, macOS, I know what I'm doing. I want everything to be logged. Please don't redact anything. So this is important to do. Otherwise, you look at the logs and you see all these private redacted messages, and they're probably the messages you actually want. So now that we have private logging enabled, what I do is I just, for example, in this case, where I'm trying to understand background task management, I install an item that's going to persist. For example, I install Zoom, because as we saw, it persists a component that the operating system alerts us. So I'm trying to gain an understanding of how this all works, what binaries are involved, how is it making the decision to display that alert to the user, et cetera, et cetera. So kick off a log, turn on logging, and then install Zoom, and we can see immediately there's some very interesting log messages. We can see the log messages are related to registering launch items. Launch items is a term that Apple kind of refers to these persistent items. In this case, we'll see it's a launch daemon. We can also see that there are two binaries that immediately are responsible or have some piece of the puzzle of background task management. The first one is SMD, and the second one is an aptly named binary called background task management D. And we'll dive into both of these. But from these log messages, we can see what is already likely happening is when the user installs something like Zoom, or if malware gets onto the system and persists itself, SMD is going to detect that some new item has hit the file system, and then somehow talk to background task management and tell it, hey, you should register a new launch item because something was just installed. So let's first look at SMD a little closer, because it is the first piece of the puzzle. So SMD stands for the System Management Daemon, and based on log messages and some reverse engineering, we can see that somehow, we don't know how yet, it gets a file system notification from the operating system saying, yo, something was just installed, process this. If we debug it, we can see that there's an XPC message that it receives with some information about the file system event. XPC is an inter-process communication mechanism. It's how different processes on macOS and iOS as well can talk amongst themselves. So if we dig a little deeper into SMD, specifically looking at its property list, we can see it has a launch event key that it specifies, which tells the operating system that it is interested in file system events, specifically in the library launch daemon subdirectory. So this is actually a neat trick. If you're writing a launch daemon or a launch agent in the property list, you can actually specify when you should be launched. And one of the reasons you can register for is when a new file appears in a certain directory. So SMD is interested in new launch daemons. So it basically tells the operating system, hey, please launch me, or if I'm ready running, send me a message whenever a new launch daemon is persisted or installed. So this is nice. SMD doesn't actually have to write, for example, its own file monitor. It can let the operating system handle that. So we can see, again, it specifies the path. And then this means when a new launch daemon comes along, the operating system will invoke SMD with information about that. So again, we can reverse engineer SMD some more. We can see, for example, that it has a method called launchd will scan path. This is actually implemented in a private framework called the BTM framework that is linked into the SMD daemon. And if we look at various pieces of it when we're debugging it, we can see that rather unsurprisingly, some of the information that is provided to it when a new item is persisted is the path of the directory where it was persisted. Now, I mentioned XPC messages a few times. We'll see that there are various components to the BTM subsystem. We've already seen SMD and the BTM daemon. And the way they communicate it is via XPC messages. So this is important because if we can observe these XPC messages, we can see not only who's talking to whom, but also when and perhaps what they're saying. So Apple ships a nice tool called LSMP. LS stands for list, MP for mock ports. And this basically will show you who's talking to whom, specifically via XPC. XPC is built on top of mock ports. And so basically, if you run the LSMP command, here we do it against the SMD daemon, we can see, for example, that the background task management daemon is talking to it, which is not surprising. We've already seen them interacting with each other. So now that we see that SMD is talking to the background task management daemon, let's take a look at this binary because, as its name implies, it's probably very central, pivotal to background task management. So we can look at its property list again. We can see some mock interfaces it exports. These are essentially XPC endpoints that other processes can connect to, for example, SMD. In the property list is also the path to its binary, which is good for reverse engineering. So let's go look at this binary. First, we do a process listing, and we can see, unsurprisingly, not only is it always running, but it's running with root privileges. So it's a root daemon that's, always up and running. If we look at its entitlements, we can see two interesting things. Entitlements are, in a nutshell, capabilities that are granted to specific binaries that are cryptographically verified and code signed. So it's a way that Apple basically allows additional capabilities to be tied to a specific binary. And one common way is a way to allow what clients to talk to what servers in terms of XPC. So a lot of XPC servers will only say, you can only talk to me if you have a specific entitlement. And we will see this isn't the case in BTM. When the XPC communications are going on, a lot of times the processes will only talk to other processes if they have these private Apple-specific background task management entitlements, which is good. They don't want random processes, tools, malware, talking to the BTM subsystem. We can also see, though, it has an entitlement to the endpoint security subsystem, which means it is able to generate and submit events to endpoint security. So this already kind of answers part of the question. That is, how do the endpoint security events get generated? Well, likely via the BTM daemon because it has the entitlement. So when it gets a message from SMD, it can alert the endpoint security subsystem and say, hey, a new process was persisted. Okay, if we dig in a little more, we can see BTM has a method called launch item registration, or rather register launch item with audit token. And if we look at this, this finally has the property list of the item that was persisted. So now we're getting somewhere. Now we're seeing exactly where the operating system has figured out what was persisted and then how to continue on. So for example, when I installed Zoom, we now see that the daemon has the path to the property list of Zoom's launch daemon that was just persisted. Let's go back to the logs to find one other piece to the puzzle, which is the background task management agent. So if we look at the log messages, we can see a log message that says, should post new container advisory, and here it's set to true. And then following that, a message posting new container advisory notification. And immediately after that log message, the user gets a pop-up on their screen, which is an alert saying, yo, something just persisted. So we now have another piece of the puzzle, the BTM agent. And so likely what's happening is that SMD is talking to BTM, Daemon talks to the agent, and then the agent is responsible for alerting the user. So let's dig a little more into the agent because it's a very important piece and something that we will attack when we show how to bypass background task management. So again, we start by looking at its property list. We can see, again, it has some mock interfaces. This is likely how the daemon talks to the agent. And also the path to the binary, which now we can take a closer look at, for example, in a disassembler, or look at the running process. So if we do a running process list, we can see that the agent is running, but one interesting thing is it's running with user permissions, not root permissions. And if we think about this a little harder, this actually makes a lot of sense because the agent is going to be responsible for showing the alert to the user, which means it has to be running in the user's session. If you're a root daemon, it's not easy. You're not really supposed to actually be interacting with the desktop session, the UI. So what you have to do is create a separate agent that runs in the context of the user's desktop session that can display alerts. Again, we look at the entitlements. We can see, unsurprisingly, some BTM-specific entitlements, and then also an entitlement related to notifications, which is how the operating system allows the agent to display not a normal alert, but a system alert that the user has to interact with for it to go away. You need this entitlement to be able to do that. Now, almost wrapping up the internals part of this discussion, but we should look a little closer at this should post new container advisory method. So this starts, again, going back to SMD and the BTM daemon. It calls a method should notify updating item. And if we look at that, it performs various checks. For example, it checks if the item is managed by MDM. If it is, it doesn't generate a notification, depending on how you've set up MDM and specified and configured that. This is good because you can imagine in a managed environment, you might want to push out a new install and not have pop-ups to all your users. So Apple thought about this and said, okay, cool, like MDM managed environments, let's provide a way to kind of override this alerting mechanism. That makes sense. There's also a few other things that are set, but ultimately this method will normally return true, which then means that the background task management daemon will talk to the agent and say, hey, you should really display an alert to the user that something new was just persisted. So let's dig a little bit deeper into how this notification is actually displayed. Basically what happens is the daemon is going to send an XPC message to the agent saying, please show an alert. When the agent gets this XPC message, it's going to process it, and it's going to use a standard notification center message to display that to the user. And we can see that, again, in the logs, including the content of the alert that is displayed to the user. Now, the last thing I want to talk about in terms of internals is the BTM database, because this will be very important when we write tools to detect persistent malware. So if we go back to the log messages, so logs are very important, we can see that there's a message that is generated anytime a new item is persisted. And that is from the background task management daemon, and it says BTMS store save to, and then some path to a file, background items -v8.btm. And if we run a file monitor, we can also see that the background task management daemon is writing to that file. We'll dig into this more, but this turns out this is the actual database that holds all the persistent items. You can imagine if you are writing a security tool, you might want to see what's in that database so that you can see everything that's persisted on a user's system. Okay, so that was a deep dive into the internals. I hope I didn't lose you too much, got into the weeds there, but it's really important for us to understand at a pretty deep level how the background task management subsystem works and also the different components, because the tools we write and the attacks we create will only come to fruition if we understand those as well. So now let's talk about tools. See if this clicker works. Not that well. Starting with talking about how to enumerate all persistently installed components on your operating system. And it should be pretty obvious, but just to reiterate, the reason we want to do this is the vast majority of Mac malware is going to persist. And the reason is if malware gets onto your system and doesn't persist, and the user reboots the system, or perhaps in some cases even just logs off, the malware's process is going to be terminated. And if it has not persisted, when the system is rebooted, the malware is not going to get executed again. So basically, it's like run once. So the vast majority of malware wants to hang around. You can imagine a backdoor that wants to connect out to a remote command and control server or something along those lines. So what the vast majority of Mac malware does is persists. Now, back in 2015, I kind of had this same observation and said I should write a tool that monitors for persistence events. So I released a tool called BlockBlock, been open source. And since 2015, every piece of malware that has persisted since then has been detected by BlockBlock. Now, this isn't like a big pat on Pat's back. It's really just to say persistence is a great way to detect malware, even brand new malware. Because as we'll see, there's some very interesting Mac malware that otherwise might be very difficult to detect, say for its persistence mechanism. And the example I like to give is a piece of malware called Dazzle Spy. This was a nation state likely attributed to China. It was targeting, if I believe correctly, human rights activists in Hong Kong, pro-democracy activists. And what was really interesting was it used zero-day Safari bugs to target macOS users. That's kind of crazy because it means that the users had to do nothing except browse to a website, and then the adversaries infected a very widespread, commonly used website that these activists were visiting. And if they visited that website, even on a fully updated version of macOS, if they were using Safari, they were owned. So it had a Safari zero-day that got initial code execution, and then a kernel bug that broke out of the sandbox and infected the macOS system. Now, I don't know about y'all, but that's scary, but also a challenge for security tools. It's very, very difficult to detect zero-day vulnerabilities because they are incredibly stealthy, unpatched, and often require no user interaction. But once Dazzle Spy got code execution on the box, what did it do? It persisted because the Chinese wanted a way to have continued access to these activist computers. And the way it persisted was via a launch agent, which is very similar to a launch daemon. So even though it used a very sophisticated infection vector, the way it persisted was very vanilla, which means if you were watching for new launch agents, you would have detected the malware, even though you had never seen it before, even though it was nation-state Chinese using zero days, simply by looking at its persistence. So here we can see that if we run a file monitor, when the malware goes to persist itself as a property list called com.apple.softwareupdate.plist, which is a big giveaway already. It's like, this isn't an Apple file. It's obviously persisting in the user's launch agent directory. Shady. That would, again, be a dead giveaway to the fact that the system had just been infected. So my goal was to find a way to enumerate everything that was persisted on a user system. The idea is, okay, I come along, someone says, I don't know if my Mac is infected or not. Am I infected with Dazzle Spy or something else? Well, if we can write a tool that simply lists all the persistent items, that's a great way to start. Because again, the vast majority of malware is going to persist. So if the system is infected, which we don't know if it is or not, the malware is likely going to show up in a list of persistent software. So it's a great starting point. So back to BTM, Apple ships an interesting tool called SFL tool. It's a closed source tool, not a lot of documentation, but it supports the command line flag, dump BTM. And if you run it, it will dump the contents of the background task management database and give you a nice list of everything that's persisting as either launch daemons, launch agents, or login items. So the majority of persistent software. That's great. But I want to do that myself programmatically. I want to write a tool that can get the same information. SFL tool just dumps it to standard out. It's not JSON. It's not programmatically easy to ingest. I want to do this natively in a way that then I can post-process more. So I began by reverse engineering SFL tool. Again, it's closed source. Apple doesn't like to do us a lot of favors with their closed source software, but we can get around this. So again, we go back to the logs. We run SFL tool, and we can see it creating an XBC mock connection to the background task management daemon. This is not unsurprising because the background task management daemon is the one that's managing the database. So if a client wants the contents of it, it makes sense for it to just ask background task management daemon and say, hey, please give me the contents of this database, which is exactly what SFL tool is doing. Okay, so I said, cool, I will just copy the code in SFL tool, write this myself, connect to BTM daemon, and it will give me a nice list of files, right? No. So this is my code, which I thought would work brilliantly. And again, in the log messages, it was like, no, you don't have the correct entitlement. So this is problematic, not super unsurprising. Kind of makes sense that Apple doesn't want random clients talking to the background task management daemon, so it kind of protects it with these entitlements. They're private Apple entitlements, meaning nobody's going to have them except for Apple, so I can't attach them to my tool and talk to the daemon. So strikeout number one. And if we look at the code for the background task management daemon, we can see it actually checks for the entitlement. So I just wanted to double check that there wasn't a bug in my code. We saw the log message saying I didn't have the right entitlement, but if we look at the binary disassembly from the background task management, we can see it's checking for that. If you don't have that entitlement, it's not going to allow you to connect. It's not going to give you the information you want. So my next thing was like, well, I know the location on disk to the background task management database. Can I just like read it myself, right? Is it some like SQLite database that I can just dump? And so I ran the file command against the database. We can see it's a Apple binary property list. And if we use the plutil command to dump this, unfortunately, we see that it is a database containing serialized objects. Serialization is a mechanism where you take an in-memory representation of an object and write it out to disk. It's very nice for computer code, but not for humans. So even if we try to dump the database, it's just all these compressed serialized objects, not human readable. Problematic. But SFL tool has a way to deserialize it, or the background task management, because it's like dumping it to standard out in a user-friendly readable version. So we just need to do a little more reverse engineering to figure out how it is doing this deserialization, and then do it ourselves. So we head back to the BTM daemon, continue our reverse engineering, and we find a method called initWithCoder. InitWithCoder is called automatically to deserialize objects. And what we can see it's doing is from the decoder object, it's basically initializing an object for various key value pairs. And if we hop into a disassembler and look for the object it's deserializing, which is called item record, we can see all the properties of this. Hooray. So what we can do then is just re-implement our own initWithCoder method, mimic exactly the same deserialization logic, and then in theory be able to deserialize all the objects in the background task management database. So, turns out this is pretty easy to do programmatically. Step one, we open the database, read in its contents. We then initialized a keyed unarchiver. This is the object that kind of manages deserialization. Then we call its decode object of class for key store. Again, this is just mimicking background task management. I looked at how it deserialized it and then basically cloned its code logic. This will trigger a deserialization of all the objects, which then we can iterate over in a simple for loop. I put this logic into a library that I call libdumpbtm.a. It's open source on GitHub, which means you can link it into your own projects, and in about 10, 15 lines of code, now parse the background task management database. Basically, you call the dumpbtm method, that will dump it to standard out, or you can call parsebtm, and that will return you a nice dictionary containing all the serialized objects. So now if we do that and run it, we get output that looks exactly like the SFL tool. Pretty cool. So for example, we can see that Zoom has persisted in the background task management database on my system, and now we have a programmatic way to pull that out. Now I mentioned this is great for security tools, so what I did is I integrated this into a tool I wrote called Knock Knock. Knock Knock is also originally from 2015. It's basically auto runs for macOS. It's one of the first tools I wrote. And what I have now done is I've taken this BTM library that I just described and linked it into Knock Knock. And so Knock Knock now has the ability to enumerate all persistently installed items, extracting them from the background task management database. And since we can do that programmatically, this gives us all sorts of extra powers. So for example, we can submit the hashes to VirusTotal. We could collect all the binaries for further analysis. Options are unlimited, because again, we now have a programmatic way to interact with Apple's proprietary undocumented background task management database. Now, that's all well and good, and Knock Knock is a great tool, but if there's one downside to it, it's that it's reactive, right? It's not going to tell you when something persists, it's just going to tell you something was persisted when you run Knock Knock. And you might be able to script it up and automate it, but said, hey, let's write a tool that can monitor for persistent events in real time. And if you recall, I mentioned block. I've been doing this for 10 years, but now we have a much better way, which is the operating system now delivering us endpoint security events, as we'll see, whenever something was persisted. The way block used to do it was monitor the file system itself when a new launch item, launch daemon was registered, parsed it out, basically what task management. I wonder where Apple got their idea. It's a great idea, though. So if we go back to the background task management daemon, we can see it has references to endpoint security. If any of you are writing security tools on macOS, I'm sure you are intimately familiar with endpoint security. Endpoint security is a subsystem frameworks APIs that Apple recently released with the sole purpose of empowering third-party security tools. I cannot thank Apple enough for this. This was the first time they were like, yeah, maybe third-party developers who are writing security tools should be welcomed in, right? Before it was like kind of a cat and mouse game. With endpoint security, Apple's basically like, yo, here's APIs. You can subscribe to all sorts of events. And with the advent of background task management, this includes events when anything is persisted, which is huge because, as we mentioned, malware is going to persist. So if we can get a notification from the operating system that something just persisted, that's awesome. Unfortunately, there's not a ton of documentation about how BTM does this. So again, back to reverse engineering. Not going to spend too much time in it, but basically it calls into the endpoint security subsystem whenever an event, persistent event occurs. And the event that it's going to then broadcast to any endpoint security clients, for example, Patrick's security tools or your EDR products, is going to be the ES event type notify BTM launch item add, blah. And so, programmatically, diagrammatically, what happens is something persists, the background task management subsystem detects that, it's going to alert the user, but also now send a message to the endpoint security system, which will then broadcast that out to any endpoint security clients, for example, your security tools, to allow you to process this event. So here's some code how to do that. I want to show you now how to write a tool that can register for these persistent events so that anytime something is persisted on a Mac system, you will get a notification. Pretty easy, and this is pretty standard endpoint security logic. Basically, you tell it what messages, what events you are of interest here. We can see number one, we're basically saying we're only interested in BTM add events. Once we do that, we then create a new client. This will have a background that is automatic, callback rather, that is automatically invoked anytime that event occurs. We will implement that in a second. And then third, you subscribe, which basically tells the endpoint subsystem, okay, I'm ready to start receiving events as they occur. So now, since we subscribe to the background task management add events, anytime anything is persisted on your Mac, the operating system will call our callback, will invoke us, saying, yo, something just persisted, what do you want to do? If we look at the endpoint security header files and documentation, we can see the format of the message that we get. It's a structure that has basically all the items we want. That is, who generated the persistent event, what was persisted, etc., etc. So I've written some code, this is just example code, that shows us basically printing out the event that is delivered to us. Because again, it's this like C structure, so we have to do some post-processing. For example, if we want to generate a message to the user or something else. But once we compile this and run this, I wrote a little tool called BTM Monitor. It's going to run listening for these events. Anytime something is persisted, for example, Dazzle Spy, even though Dazzle Spy is using 0 days and kernel bugs and sandbox escapes, we almost don't care about all that fancy stuff. As soon as it persists, we now get a notification that we can parse out, see who installed the persistent item, and then more importantly, what was persisted. So we can see that kind of in the bottom of the terminal output. We can see the path to the binary. It's something called software update running from a hidden directory. Huge red flag. And again, the path to the persistent property list is in the launch agents directory, the user's launch agent directory, but it's called like com.apple something. So again, huge red flag. I don't show this here, but if we go examine that binary, it's also unsigned. So we have an unsigned persistent binary running out of a hidden directory from a property list that claims to be Apple. Like, yeah, malware. So at this point, we've essentially, in theory, thwarted this zero-day attack simply by leveraging these new persistent events. So, awesome. One takeaway, there is a BTM event, endpoint security event for removals. It's broken. Doesn't work. I don't know why. Apple, if you're here, please fix it. But I don't really care that much. But I guess you could, if someone deleted your security tool that was a launch daemon, it might be nice to know that. I don't know. Now, as I mentioned, the removal was broken, but so was the ad. So when Apple released this, I was like, hooray, like my life is so simplified. I can just use Apple's new notifications. I can refactor my programs and throw out like 80% of my code, which is the best feeling in the world. And I was like all excited, wrote this tool, ran it, started testing, and I was like, hey, nothing's working. What am I doing wrong? Well, it turns out like this was badly broken. Two ways. First, anytime a new item was persisted, the add event would fire, but it would fire for every event. So you would just get this long list of everything that was already persisted, and it wouldn't tell you which one was new. So I was like, ugh, not helpful at all. And then for login items, which are another type of persistence mechanisms, you basically have launch agents, launch daemons, and login items, you would get no alert at all. So if malware persisted as a login item, even though you had registered for the BTM add callback, it wasn't firing. So I submitted this to Apple. They were like, yeah, this is by design. And I was like, really? And eventually they fixed it. But so there were some issues. So I thought, okay, well, there's smoke, there's fire. There's probably still some issues with the background task management subsystem. And to me, this was really important to look at and dive into because on one hand, we have Apple telling us that they have released this amazing new security feature that will alert the user whenever something persists and empower security tools with notifications anytime something persists, which is great. And if that is true, we are stoked. But is it? I thought, okay, we should really look into this because Apple really doesn't have, in my personal opinion, a great track record backing up their security claims. And this is not to pick on Apple per se, but it is really important when a security mechanism is marketed. If it doesn't meet those goals, that's actually very problematic because we might be utilizing them, for example, to build security tools, or users might be depending on them. And if they don't fulfill the goals they claimed, we are all under a false sense of security, which is actually very problematic and can put us at a severe disadvantage. So let's now look at some issues of BTM that impact both the alerts that are sent to the users and also the messages that are sent to the endpoint security subsystem. Now, you can imagine from a hacker's point of view, they are not stoked about BTM. Imagine you are the Chinese Dazzle Spy authors. You got your sweet 0 days, you're hacking, pro-democracy activists in Hong Kong, you're feeling really good about yourself, right? You're infecting all these Mac systems, but now you're getting detected because of Apple's new security mechanisms, right? There's an alert that tells the user, hey, something was just installed, and yes, the average user might ignore that, but some users will be like, hey, what gives? They'll call up Patrick or their friendly Mac professional, their Mac admin, and say, what is this software update pop-up? And eventually it'll lead to the malware infection. Better yet, if they have any security products installed that are utilizing these new background task management alerts, these security tools will get notifications about something was just persisted. And as we saw, Dazzle Spy, it's running from a hidden directory, it's unsigned, it claims to be Apple. That's actually pretty easy to heuristically determine that that's malware. So hackers not stoked about background task management. So if we put on our black hats and pretend to be the adversaries, we're trying to basically solve two things here. How do we prevent the alert from being shown to the user? And how do we prevent the endpoint security message being sent to security tools? Now, one important thing, these are two totally separate events, in the sense that if you find a way to suppress the alert, the endpoint security message will still be delivered. If you find a way to suppress the endpoint security message, the alert will still be shown. So they are exclusive events. They are unrelated, not logically tied together at all. So we're going to need two separate attacks. Now, the first attack, and I don't even think this is an attack. It's not anything super special, is the fact that BTM only monitors certain items of persistence, specifically launch daemons, launch agents, and login items. Now, the vast majority, anecdotally, I would say 95% of Mac malware that persists will persist using these mechanisms. So in that sense, it's very comprehensive. But it's good to know that this is all it's monitoring, and so if malware wants to persist in another way, that will be outside the view of background task management. So for example, Enigma persists as a cron job. Cron jobs are not currently monitoring by BTM, so BTM's not even coming to the picture. There's some other great research here by some other great researchers, for example, Chava, who has done a really good job articulating other methods that malware can persist. So check out his blog. He has something like 30 other ways to persist. Amazing. The most recent one he just wrote about, doctile plugins. Awesome. BTM is not monitoring this. In theory, malware could persist as a doctile plugin. Very stealthy, not monitored by BTM. So BTM wouldn't come into play. So this is really not a vulnerability in BTM. It's not something we should get super excited, but it's important to understand the limitation of it. Now let's talk about some specific attacks, though, against BTM. This first one I love. It's hilarious. So back to the SFL tool. This is shipped in all versions of macOS. It has a reset BTM command line option, which is fine. The idea is if the database gets corrupted, you could reset the database, clean slate, awesome. The problem is when you run it, it puts BTM into this like funky state until the box is rebooted. And that funky state basically means if anything is persisted after that command is run, it will not generate an alert to the user. And we can actually see this in the log messages. It says, should post advisory, and that's set to false. Now, I don't know actually what goes wrong. All I know is if you reset the database and then persist an item, the item will be correctly persisted, but no alert will be shown to the user. So I love this attack because it's not some crazy buffer overflow, heap corruption. You're just using Apple's tool. So clearly there's an issue here with the way that they handle the resetting of the database. And note, this doesn't actually impact system functionality. As soon as the box is rebooted, the database is automatically rebuilt, including any new items that were persisted after the reset, but no alerts are ever generated. So it's not like when you reboot, there's a new alert. So this is a neat way. One problem is it requires root privileges to execute. So I was like, okay, this is a neat attack, but I want more. I want something that a normal user, a piece of malware running with average permissions can utilize. Okay, so back to all the pieces of background task management. We have the background task management daemon, and we have the agent running with user permissions. This is important. That displays the alert to the user. So my thought was, well, the agent is essentially getting this XPC message from the daemon, and then it turns around and generates a notification to the user. So what if I just tell the BTM agent to take a nap, like sleep, chill, persist something? Yes, this will cause BTM daemon to send a message, but if the agent is sleeping, it's not ever going to actually process that message and display that to the user. And so that's exactly what we can do. 3 easy steps. We get the process ID of the background task management agent. We send it a stop signal, which puts it to sleep. We persist the item. The alert is never shown because the agent who is responsible for displaying the alert is taking a siesta. And then once persisted, we actually then kill the agent, which we can do because it's running with user privileges. The reason you have to kill it is if you resume it, that XPC message is actually queued, and as soon as it wakes up, it will display it. But if it kills it, it goes away, and that message is dropped. No alert to the user. Hooray. So we've shown how to very easily bypass the alert that's sent to the user. I also, though, wanted to find a way to suppress the endpoint security message that would be delivered anytime an item was persisted. And to me, this was more important because from a hacker's point of view, it's more likely they're going to be detected by a security tool and that new persistent event versus some user noticing an alert. So I looked a little deeper. Again, we talked about the background task management daemon and how it is responsible for delivering the alert to the endpoint security subsystem that then is sent to endpoint security clients. I reverse engineered that. There's a method called submit item add to ES that calls some notify blah, blah, blah. Eventually calls down call notify only, which ultimately calls into the kernel to process and deliver the endpoint security event. So I was like, we have to go into the kernel. Oh, that's fine. I have a lot of free time. So I looked at the implementation for the delivery of the message, and I noticed some interesting things. I could spend like an hour talking about this slide. I will try not to. The idea is the endpoint security kernel extension is going to try to look up the process that is responsible for the persistent event. If you remember the message that's delivered, one of the pieces of that is who was responsible for generating the persistent event. And that's all well and good. That's very important information. But we can see what's happening is it calls the proc_find API. This is a kernel API that, given a PID, will give you back the process object in the kernel. This is all well and good unless the process has exited. If that happens, what proc_find will return is a null, a 0. It's basically like, that process is gone, I don't have a process object. Okay, fine. They don't check that, they continue on, and they call proc_get_executable vnode. The problem is, if you call that with null, the kernel basically says, you're calling me with a null process object. I don't really know what that is, so way I handle that is I return to you, sorry, I'm going to back up a second. Proc_find, if that gets called incorrectly, it will return a it will return a process object that relates to the kernel. And then when you call get_executable vnode on the kernel is not backed by a normal running process, so that is going to error out and return no such process. So we can see that in what normally happens if we persist something like one of my tools, for example, oversight. We can see that normally it finds that process and returns that. But in the case where the process is not found, there's a problem. And this slide explains better what I was just trying to explain, which is if proc_find is called with null or 0, if the process is exited, it returns the kernel task. The kernel task does not have an executable file backing it, which means there's going to be an error message. And we can actually see this if we find a way to trigger this in the logs. We can see at the very bottom it says fail to submit event using ES_syscall20. That's the add BTM event. 3, no such process, which maps back to that RAX equals 3 in the kernel, which basically saying the kernel couldn't find the process that was responsible for the event. Okay, so I thought, how do I write a proof of concept that could persist an item and then very quickly exit? And I was like, wait a minute, this is what my utility does. Block installer executes CP to copy its launch daemon property list to the launch daemon directory. CP is a very quickly executing command. I wonder if essentially there's a race condition between when CP exits and when the background task management daemon tries to process that. And so I said, let's try that. And so I'm going to do a live demo, which is risky-ish. Oh, wait, how do I get out of here? Control P. Escape's not working. Oh, no. H? No, keyboard. Okay, hold on. Can I like unplug this and then plug it back in? I think the clicker like took over. Okay, I'm gonna unplug this for a second. Come back. I promise the demo will be worth it. Oh man, it's not letting me exit this presentation. Oh no, malware. Okay, you know what? We'll do that. We'll do it at the end of the presentation. This is the first. Okay, I'm coming back. Wow, I didn't even get to try the demo. Savage. Okay. Well, I'm going to try to go back a few slides. Come on, keyboard. I feel like my keyboard's dead. Okay, well, I skipped like one slide, but basically it was a slide explaining the demo, and then a slide saying we're now going to talk about how to detect the bypasses I just showed you. So remember, the first bypass was resetting the database using the SFL tool with the reset BTM command. So one very easy way to detect this is if you have a process monitor running, because I can't think of a legitimate reason why this undocumented tool should be running with the reset BTM command. So you can basically monitor for this or actually block this command altogether if you have a tool that's capturing events. Oh, no, are we really not hanging? Man, I just updated to Sonoma this morning. Okay, wow. Oh, there we go. Okay, so the keyboard work, or the mouse works. The keyboard is foobarred. Okay, so the next attack we want to detect is the attack where we put the agent to sleep by sending it a sig stop command. Again, this is not something that's normally happened. So what we can do is we can actually leverage the endpoint security framework. It has the ability to monitor signals sent from one process to the other, which is a very powerful capability. And not only does it have the way to monitor these signals, it actually provides a way for you to authorize signals. So what you can do is actually register a callback that says, before any signal is sent from process A to B, call me, and I will tell you if that should be allowed or not. So that's exactly what we do. We basically monitor for the signals, and if one is sent right here, that belongs to the, it's a signal being sent to the background task management agent, and it's a sig stop signal, because we can see who the target is and also what signal is being sent. We return this ES auth result deny, which basically tells the operating system, do not allow that signal to be delivered. So in that case, if we run that, and then we try to perform our attack, sending a sig stop command to put the agent, whose PID in this case is 590, to sleep, that will fail. We will detect and block that. The last thing we can do is monitor for persistence altogether. I showed you the BTM launch item add endpoint security message is easy to bypass with a quickly exiting process. But other endpoint security messages are not impacted by this. So it seems like that fault is only in the BTM launch item add message, the new message they recently added. So, and this is exactly what block unfortunately still does. It monitors the file system. So when something persists and copies itself to the launch daemons directory, block or any third-party security tool can monitor for file system notifications. We'll get an alert and then can go examine that and detect and block that. So basically, don't rely on the BTM launch item add endpoint security message. Maybe fall back to, for example, the file events. All right, conclusions and takeaways, and then we'll try the demo. So today we talked about understanding the internals of background task management. The internals themselves, maybe not the most exciting thing to talk about, but they gave us a lot of foundations and understanding that then allow us to build some very powerful malware detection tools focusing on persistence, which I've really tried to drive home is a great way to heuristically detect even brand new, very advanced nation-state Mac malware. But unfortunately, a myriad also we showed of bypasses against this. And this is also one of the takeaways I want to kind of drive home as well is, not to knock on Apple too much, but it's rather unfortunate when they release a new security framework or new security technology, they don't even seem to test it very well or think about it from an adversary's point of view. And I think there's a lot of improvement there. And if people such as myself and other Mac security researchers are not pulling this apart and pointing out these flaws to Apple, like, who is? It'd be naive to think that the adversaries aren't doing this exact same thing and laughing all the way home, because now users might be saying, I don't need third-party security tools because the operating system will alert me anytime something is persisted, which is understandable for the user to think. But if that's trivial to bypass, the hackers are going to be stoked that the users are thinking that because they are going to be silently persisting continually. So definitely some room for improvement there. Just another takeaway. If you're interested more in reverse engineering, malware topics, I've written a whole book on this. It's fully free, open source at tao.org. You can also purchase it. All royalty payments go back to the foundation. And I am in the process of writing volume 2, which is going to be very similar to topics we talked about today. For example, there's a topic chapter on persistence, which provides the code and techniques we talked about today. Speaking of the foundation, just want to briefly mention it. Again, we organize the OBTS conference. We also provide college scholarships to students. We have some neat diversity programs. If you're a company that wants to get more involved in the community, definitely check out objectivec.org. Again, we're a fully 501c3 organization doing all sorts of cool stuff. And lastly, I want to thank the amazing companies who make all of this possible. These are the companies who sponsor, support the nonprofit foundation. A lot of them are here today. And they allow us, for example, to organize our Mac Security Conference, release these free open source tools, work with students around the world. So I just wanted to end by thanking them. Again, thanks to you all. And Patrick, I will take questions. And I'm going to reboot my computer and show you an awesome demo. So thank you.
So we are, well, you have 10 seconds to ask questions.
Yes.
Well, we have one here.
I don't mind staying a few minutes late. We can also talk more at the at MacPaw's awesome pool party, which you all should come to. But feel free to ask away here, too.
So if I remember rightly, Ventura introduces a new way of persisting where the login item has to be created within the app bundle. How does Background Task Manager interface with those? And what can you do to detect them going forwards?
Great question. So just to repeat briefly, Apple is recommending now that instead of persisting as essentially external launch items, you do that within the application bundle. From a security point of view, that's great, because it means that if an adversary tries to tamper with those items, it'll corrupt the signature of the application bundle, which is very easy to detect. I believe this is one of the main reasons they introduced background task management. They said, look, there's so many ways to persist. We're moving now to these app bundles. Let's build one subsystem that manages and governs all of these. And also, by the way, we will then generate this new endpoint security message. So regardless if the software or malware still persists in the old way or the new way, there will be one message that's sent out to security tools, which is great. Because otherwise, I was going to have to go update block and now start looking at application bundles. It was going to get complicated. So I believe, and I haven't dug into this a lot, but I believe that that goes in lockstep with BTM, basically the new launch agent packaging bundling that Apple is recommendation. So great question. In theory, once they get the BTM stuff all figured out, it'll seamlessly all work together. Great question. Yes, third row, fourth row.
Hi, thanks for the great talk. I was wondering, the last time I checked, you need an entitlement to use the endpoint security thing. So it's, well, basically up to Apple to decide if you see those events or not, right?
Mm-hmm. Yeah, so the question was regarding kind of the endpoint security messaging, the processes exiting, et cetera, et cetera. They seem to do it in the other endpoint security APIs. I haven't reverse engineered it fully because it's a kernel extension, and I guess I don't have that much free time. But for example, for the file system event notifications, those always have the correct PID, even if it's exited. So either that's being handled better, cached, or something. So they already have it figured out over there. I think the, hypothesizing here, when they introduced the new endpoint security messaging for the BTM one, they didn't think that through. It wasn't tested as much. It was written by someone else. Who knows? But there's not parity in terms of handling quickly exiting processes, which is problematic for the new messages, whereas the old ones don't seem to have that issue. And that's always frustrating. I'm like, y'all solved this already? Why? You just broke it again. Come on, we're not moving forward here. Okay. Yes, one more question, 4 rows back. And then we'll do the demo, and we'll chat more at the pool party.
Yeah, just real quick, because I'm curious, but why do you need to send a stop signal to the background task management agent? Can't you kill it directly?
Great question. So the question was, why can't you just directly kill the background task management agent that's about to display the message? And I tried that first because I thought the same thing. Turns out it's started on demand if it's not running. Basically, the daemon sends an XPC message to deliver or wake it up or start it if it's not running. And so if you kill it, and persist, it probably is going to have restarted already. So if you send it a stop and tell it to sleep, the message actually gets like kind of delivered and then queued up somewhere. And so that's why I mentioned if you then start it, the message actually gets displayed. Whereas if you kill it, I think the daemon or the mock subsystem is like, well, we delivered it already. It's maybe queued over here, but we did our best effort. So if you kill it then, even when it restarts, that message has essentially been lost to the ether. So good question, though. OK, quick demos. And I mentioned I just installed Sonoma, and all this research was done on Ventura. So maybe Apple's patched these things. We'll see. OK, so the first thing we're going to do is I just want to show you SIP is enabled. This is running, yeah, Sonoma. We'll start logging, and we'll look for the failed endpoint security alert. We'll also come over here, and we'll use Apple. OK, the first thing I'll show you is that this property list doesn't exist. This is this is BlockBlock's property list. This is not malware. This is just what BlockBlock is going to create and install to persist itself. So in theory, if the background task management endpoint security message is delivered, we should detect this when that property list is created. So we're going to start Apple's ES logger. This is a tool that can allow you to listen for events. So we're listening for the add event. We're now going to install BlockBlock. This is not malware. This is my tool. And we're going to see that the alert is going to be shown to the user. We'll get to that in a minute, because again, those are totally separate. But what we shouldn't see, and what we don't see, is no message was delivered to the ES logger, which is a client that's listening for these messages. Also, if we go back here, we can see that the operating system just told us, hey, I failed to submit this event because of the aforementioned reasons of the copy command exiting before it was able to get the PID. So strike one, Sonoma. That's still not working. And just to confirm that, like, I'm not just making this all up, we can see that if we look, that file is now there. So we basically installed a launch daemon. The user was alerted. We'll get to that in a second. But the ESF, the endpoint security message that's supposed to be delivered is not. Yikes, not good. OK, next attack. Let's show how to suppress that message. So I'm going to, kill this. I'm going to uninstall BlockBlock so we can do this again. You can imagine, I should probably have some persistent malware, but I'm running this on my own machine. OK, so BlockBlock is installed. It's gone. OK, so what we're going to do is we're going to, from a normal user prompt, we're going to get the process ID of the background task management agent. We're going to tell it to go to sleep. You do that kill, sig, stop. Stop, can't spell. OK, now it's sleeping. If we do a PS on this, we can see it has a T here, which means suspended, apparently. So now what we're going to do is we're going to install BlockBlock again, which is going to persist a launch daemon, which in theory should A, generate an alert, B, a message. So BlockBlock is happy. There was no endpoint security message, and there was no pop-up. Now, I can prove that to you because if I resume the endpoint background task management agent, we will see the message. Now, malware authors would obviously never do this. They would just kill it, and it would go away. But if I do this, oh, am I lying? Where'd it go? Sometimes it gets into a super funky state. Oh, I killed it. Oops, my bad. I was supposed to resume it. But, well, hey, the message never showed up. But the point is if you stop it, perform the attack, and then resume it, the system alert will get shown to the user. So do what I just did, pause it, persist, and then kill it, and then the message will never show. Now let's do the last one, which is reset the database. I mentioned you need root privileges to do this. OK, we reset the database. The database is totally foobarred. If we uninstall BlockBlock and reinstall it one more time. And I'm going to run the reset again, just to be sure. In theory, again, we'll see how Sonoma handles all this. We shouldn't see anything. So I didn't have to the agent is going to be running again, maybe. Now, because the daemon's database state is foobarred, so it didn't even try to contact the agent to restart a new version. So again, if you reset the database, which is the third and final attack, the BTM daemon's basically like, I'm done until you restart the system. So after you execute that, apparently even on Sonoma, malware authors can persist away to their heart's delight. The endpoint security message will not get delivered in any case, and the alert won't get shown to the user. So this is kind of, in my opinion, maybe the more problematic one, because we just ran Apple's tool, and it just broke everything. Like, we didn't have to pull off some crazy exploit. So, thanks for watching the demos. Apple, if you're here, please fix this. I mean, I've submitted lots of bug reports. And again, thank you all for attending the talk. Thank you to Patrick again. Super stoked to be back in person. Maxis admin, great conference. And yeah, round of applause for y'all, for Patrick.
Thank you.